Hi, it's Mr. T here. In this video, I'm going to review how we carry out tests to identify organic samples. I have over 20 years of experience teaching both chemistry and physics in senior high school. I want to share my expertise to help you master the coursework. Now, how often have you gone through your lab at your chemistry class just to come up with an epic fail? Well, today I've set up a video that can go through each one of these tests and see what should have happened when you did that experiment. Right, let's crack on and find out how to carry out these important identification tests. Okay, so let's look at our first type of organic molecule we might want to identify, and we can use a bromine water test. Now, a bromine water test will undergo a reaction with an alkane. So what we do is we take a sample of our alkane, and we take some bromine water, which is just bromine dissolved in an aqueous solution, and we add it to the mixture. We give it a shake, and lo and behold, what we get is we get the same. We haven't had any reaction if we just have an alkane. So this is kind of a negative identification. So however, if we take this and we put it in sunlight, the UV light from the sunlight will catalyze the reaction, and we will see it go colorless after about 30 minutes in sunlight. Now what's happened here is we have our alkane and the bromine has come along and it's substituted a hydrogen here. And so this alkane has undergone a substitution reaction. Now I want you to take note here, this is not a distinguishing test for alkanes. Any organic compound that has carbons and hydrogens will undergo this reaction. So it's just a test that we can use when we're going to talk about and comparing it to alkenes. So let's look at how alkenes go with bromine water. Same thing, we take the sample. Bromine water, add it, we get the orange solution, orange brown, give it a shake. Okay, shake, shake, and there you go, colorless. Now this colorless happens just in a few seconds, depends how quickly you shake that test tube. This is a positive test. What we would say here is the solution changes from orange to colorless. This is the positive test for an alkene, but it's also a test for an alkyne. It's a test for unsaturated hydrocarbons. Okay, so here's an example of what happens here. We have a double bond. You can see that double bond there. It's broken, and now the two bromines from our bromine water have added to the place where the bonds are broken. So this is called an addition reaction, and the alkene is turned into a haloalkane. Okay, we can do another test to distinguish alkenes, and it's called the permanganate test. And in this test, we're going to take the sample, we're going to add some potassium permanganate, or just permanganate. I guess it could be sodium permanganate, don't see that around much. And to the sample, it's purple solution, but if I shake it, it goes brown. So it goes from purple to brown. Now sometimes you see people distinguish, say in this test you can add acidified permanganate and you put it in there and it goes from purple to colorless. But look, I love just adding permanganate and getting this brown color. This is a positive test for alkenes or for unsaturation. The solution changes from purple to colorless. Now this is a different type of reaction here. The permanganate is an oxidizing agent. So what it does is it does break this double bond, but it adds oxygens in the form of hydroxyl groups to it. So this is the alkene has undergone an oxidation reaction, and now it's produced something called a diol. Okay, so you can see it for a start we had propene, and then afterwards we had propan 1,2-diol. Okay, let's have a break. So this is right, let's look at our first fun fact. Okay, alkenes, they're good for you. What do I mean by that? Well, here's two examples of fats or oils that we might use in everyday life. On the left is some sunflower oil, and on the right is some coconut oil. Now, what scientists have found out is that if you have unsaturated oils, you lower your risk of heart disease. And if you have a diet with lots of saturated oils, you increase your risk of heart disease. So one of these fats, one of these oils, has lots of unsaturated fats, and one has lots of saturated fats. Which is which? So sunflower oil, 94% unsaturated fat. Unsaturated fats, lots of alkene functional groups in there, really healthy. 92% saturated fats for coconut oil. Okay, so this is not going to be good for the condition of your heart. You might want to reduce the amount you have. Maybe don't get the coconut cream in your latte, right? This increased risk of heart attack. Right, let's get back to our tests. Alcohol. Okay, so if I want to test the presence of an alcohol group, usually I use acidified permanganate test. Now this test is for either primary or secondary alcohols, but not for tertiary alcohols. So I take a sample, I add some acidified permanganate. So this time acidified permanganate is permanganate that has some acid that's been added to it. So that's what the slash with the H plus means. That means acid has been added to the permanganate, and that facilitates the reaction. So I add that to the solution, I get a purple solution. You know what? This one doesn't always react straight away, so we take it and we put it in a bath that's been heated up by a Bunsen burner called a water bath. We put it in there, we sit it in there for 5 minutes, and boom, there it goes clear. So this positive test for this is the solution changes from purple to colorless. I said clear, but I should have said colorless. There is no color there. You know the purple color is actually clear for a start. Okay, so here's an example of the reaction there. We've got an ethanol there being heated with the permanganate H+, and it's producing the carboxylic acid. Now notice this is a primary alcohol because the OH is attached to a carbon that only has one other carbon attached to it, and this undergoes what's called an oxidation reaction to produce a carboxylic acid. Just a wee side note here, there is actually an intermediate that is produced halfway between these two, and that's called an aldehyde. Okay, if we actually have a secondary alcohol, we can see there that it's a secondary because the carbon that's attached to the OH has two other carbons attached to it. We produce something called a ketone. So this is still an oxidation reaction, but our secondary alcohol has been turned into a ketone. So we can actually do the same type of reaction, but we can use a different solution. It's called acidified dichromate test. So we take our sample, we add acidified dichromate. Again, you can see it's acidified because it's got that wee / with the H+ next to it. We're going to take this orange dichromate and we're going to squirt it in. We make an orange solution. Again, bit disappointing, doesn't react straight away. So we're going to take that water bath, we're going to chuck it in, we're going to heat it for 5 minutes. And this will go a blue color. Well, it goes green. It goes a greeny blue. Now the reason it goes a greeny blue is because if there's still some orange left, it mixes with the blue and it makes it green. But if you see a bluey green color, okay, if it goes from orange to blue green, positive reaction, you've got an alcohol there. You know what? It might not be an alcohol, it could be our aldehyde, but it's usually used for an alcohol. So if we take a primary alcohol, like before, we're going to turn it into a carboxylic acid. And this is also an oxidation reaction. If we take a secondary alcohol, we're going to turn it into a ketone again. And this is also an oxidation reaction. Okay, so sometimes we want to identify a tertiary alcohol, but that last test, it doesn't tell us whether there's a tertiary alcohol there because it doesn't react with tertiary alcohols. So we're going to do this thing called a Lucas reagent test. Now, Lucas reagent is in NCA, it's just called concentrated hydrochloric acid, but in reality, it's concentrated hydrochloric acid and you add a bit of zinc chloride to it as well. But we're only going to write down here concentrated hydrochloric acid. We're going to add it to our sample. So remember, the bottom sample is our tertiary alcohol, and we're adding our concentrated hydrochloric acid. It goes cloudy. It'll go a cloudy, whiter, cloudy color when you add that. So you give it a shake and it goes that cloudy color. Now actually, if it was a secondary one, you could take that and heat it for 30 minutes and it might go cloudy, and then you could identify a secondary. But sometimes it's just easier to do the other test. So positive test for this observation is a tertiary alcohol. The solution goes cloudy quickly. So notice a tertiary alcohol, the carbon that's attached to the OH has 3 other carbons attached to it. Now this is a substitution reaction because the chlorine from the hydrochloric acid is replacing the hydroxyl group from the original tertiary alcohol. And it's producing what we call a haloalkane. Okay, another fun fact. Fun fact of the day. Let's have a look. Alcohols taste sweet. What? No, I've had alcohol before. Well, some alcohols are sweet, I guess. But, okay, here's an alcohol. This is called glycerol. It's not the alcohol that you might drink in an alcoholic beverage, but it is found in lots of food products. It's used as a sweetener. It's used in makeup. It's used in lots of different, toothpaste of all things. Now, the reason it's 60% is sweet is sucrose. That's just table sugar. The reason that it's sweet is the receptors on your tongue buds, the buds on your tongue, sorry, they can detect the OH groups, so they taste a wee bit sweet. That's glycerol. So this one here is glucose. It also tastes sweet, but it's like 117 sweet as sucrose. It means it's more sweet than sucrose. And some people even say if you take pure ethanol, that's the alcohol that they put into alcoholic beverages, and you just mix it with pure water, that you get just a slight sweet taste from that as well because of the OH group. Because OH or alcohols taste sweet. Okay. How do we test for amines? Well, we use red litmus paper test. So what that means is we actually take a sample of water and we add the amine to it, boom, and we just give it a swirl around until we've got a mixture here, and then we take that mixture and we add some red litmus paper. And remember that red litmus paper, if it's going into a base, it's going to turn purpley blue. So our positive test is that red litmus paper goes blue when we've added to an aqueous sample of amine. So we have to make sure that we add the amine to the water first. It doesn't work if you haven't added it to the water. Now the reason here is that when you add the amine to the water, it produces this hydroxide ion, and it's a hydroxide ion that reacts with the red litmus paper. So amines are weak bases and they partially dissociate when we put them in water, and they produce these hydroxide ions that then will turn litmus paper that blue color. Odours, amines. Well, amines, you can sometimes detect them from their odours, but it isn't the perfect way to detect them, but they have a fishy smell. Okay, so small amines smell like ammonia, but the bigger that you get on the chain, the more fishy they smell. The other thing is quite nasty is if you have these double amines or these diamines, you get these very, very bad smelling chemicals. On the left, you've got this one called putrescine. You can understand what sort of smell that comes from. I mean, that word putrefaction, which means rotting dead flesh, that's what it smells like. And cadaverine, another name there, which means that it's the smell that comes from dead bodies, from cadavers. So these are the smells that are associated with rotting fish and meat. Now they're caused when bacteria break down amino acids. We usually don't use these to identify amines, but look, if you smell that sort of off smell, or your fish is a bit old or whatever, you're going, I know what that is, that's an amine. Okay, aldehydes. Aldehydes, we use a solution called Fehling's, but the biologists call it a Benedict solution. It's basically the same thing. They do exactly the same reaction. They are basically a copper solution in hydroxide. So we take our sample of our aldehyde and we add Fehling's solution to it. Boom, it goes blue. And then we just give it a wee shake and we place it in the water bath. We put it there for 5 minutes, and what we get is we get a brick red orange color. So this is actual the Benedict solution test you might have done when you're in like year 9 or year 10 to test for the presence of sugars, because what actually happens is the glucose you're testing for has an aldehyde group on it, so you're really just testing for an aldehyde. Now what's actually this positive test here as it goes from blue to orange, what's actually happening here, oh golly, orange is spelt wrong. So here we go, here's our solution, our reaction here, aldehyde on the left. What's actually happening is the blue color from the copper ions is reacting with the aldehyde, and the aldehyde is being oxidized to carboxylic acid, and in the process the blue copper ions have been reduced to copper 1+ ions, which when with oxygen have an orange color. Look, aldehyde undergoes oxidation to carboxylic acid. Important thing here, use Fehling's solution and aldehyde will turn it from blue to orange. Okay. Okay, so here's another test for aldehydes, the silver mirror test. Now the Fehling's test and the silver mirror test, or if we go back to the Fehling's test, we also called it the Benedict's test, right? So both of these are designed to work with an aldehyde, because an aldehyde, when it is oxidized to a carboxylic acid, it isn't a strong enough reducing agent to change our permanganate away a dichromate. It won't react with them, so we need specific reagents that will react with aldehydes. And the first one that we'll use here is a Tollens reagent. So before we can do the silver mirror test, I have to produce some Tollens reagent, and usually have to produce it fresh. So to do that, I take a sample of silver nitrate, I put it into a test tube, and what I'm going to do in this test tube that I have here, I want to add some sodium hydroxide to it. Now add the sodium hydroxide until I get a brown precipitate. So I add the sodium hydroxide and then I get a brown precipitate. Now once I have that, I'm going to get some concentrated ammonia and I'm going to add that to this brown precipitate until it just dissolves. So you add it, you're shaking, you add it, you're shaking, and it goes clear. Now I have a solution of Tollens reagent and I can go on and make the silver mirror. So this silver mirror, I need a very, very clean beaker or test tube, or I love to use the glass Coke bottles because you get the inside of the Coke bottle and it gets silver and it looks amazing. So I take the Tollens reagent, I put it into this very clean glassware, and I'm going to add my sample of my aldehyde here. So add a sample, and then I have to gently heat it in a water bath for 10 minutes. If you do everything just right and you hold your mouth right, it goes silver mirror. And you get the inside of your glass coated with a silver mirror. And if you do it well enough, it's coated so well you can see reflections in it. Now, this is a positive test for aldehydes, and it's an easy one to remember because of the strong silver mirror. What's happened here is our aldehyde functional group has been changed or oxidized into a carboxylic acid. At the same time, the silver plus ion was reduced to silver metal. So the aldehyde has oxidized to a carboxylic acid. Okay, time for another fun fact. Okay, did you know that losing weight, you get fruity breath? What? How does that work? Okay, so you've seen people go on keto diets. Well, sometimes if people go on keto diets or reduced calorie diets, they get a process called ketosis happening. Now, ketosis means if there is not enough carbohydrates in your diet and your body isn't getting enough glucose in its bloodstream, it will start to break down fats in your liver, and in that process it produces some ketones. Now, one of the byproducts of producing the ketones is that you produce a ketone called propanone. And propanone is very volatile. It means it evaporates very easily. It evaporates out of your lungs and it comes out of your breath. And it smells fruity. So, hey, that's good. Losing weight, fresh smelling breath. Okay, carboxylic acid, blue litmus test. Okay, so a couple of tests for carboxylic acid. So one of the easier ones, I guess, is you take some water, you add your sample of carboxylic acid, you shake it till you've got a solution. You then put some blue litmus paper in there and it goes pink. Now, this happens because, remember this is blue litmus paper goes red, because our carboxylic acid functional group, well, our carboxylic acids are weak acids, they dissociate or partially dissociate, and they produce these hydronium ions. And these hydronium ions are basically acid ions, and they are what produce, what reacts with the blue litmus paper to turn it red. So because the carboxylic acid partially dissociate. Okay, so now we've got another test for carboxylic acid, much be more definitive test. So in this test, what we do is we take a sample of our carboxylic acid and we're going to add to its solution, an aqueous solution of sodium carbonate. So when we add the sodium carbonate, we get this effervescence, or all of these bubbles produced in the solution. So our observation here, the positive observation for carboxylic acid, is the solution fizzes or bubbles when we add sodium carbonate to it. Now what's actually happened here is we've basically just taken an acid and reacted it with a carbonate to produce our salt plus water plus carbon dioxide gas. This reaction here isn't balanced, but it does show what's happening. Okay, so let's have a look at another fun fact. Fun fact of the day. So, the foulest smelling carboxylic acid. Okay, so carboxylic acids, there's a really foul smelling one there, and it's actually associated with dairy products. So in all dairy products, we've got this fat molecule here that has glycerol attached to, by esterification, to butanoic acid. Now 6% of the butter is made of this solution here. Sorry, this made of this fat. When this fat is put inside our body into our stomach, which is a kind of a watery, acidy mixture, it undergoes this reaction called hydrolysis that breaks apart the molecule at the oxygen. Okay, when it breaks apart the molecule, the oxygen, it produces butanoic acid. Now, butanoic acid, you just get a drop it on you when you're making esters in the lab, and you will smell bad for days. It smells like baby puke. It smells like monkey vomit. Basically, the smell is rancid butter. It's when this fat that's in butter breaks down to form the acid, we get this really smelly chemical, and it's called butanoic acid. You know, just as a side, it actually, if you only smell a wee tiny bit, it smells fruity, a bit like bananas or a bit like pineapples. It's weird. Yeah, but it does smell like spew if you get too much. Okay, acyl chloride. So the test for that is a water test. What do I mean by that? Well, we take a sample of water and we add just a drop of acyl chloride, because this is going to vigorously just react. It's just going to go tss, right? And it's going to produce a vigorous reaction because acyl chlorides are very reactive molecules. Then that gas that's evolved off, we're going to test it with damp litmus paper. You take the litmus paper, you put it under the tap, you get it wet, and you hold it over the top of the test tube, and it goes pink. Because there's hydrochloric acid gas, hydrochloric or HCl gas coming up, and when it hits that damp water, it makes hydrochloric acid that turns the litmus paper pink. So the positive test here for acyl chloride is it reacts vigorously with water, and the gas, when it's tested, turns blue litmus red. Now, the reason that happens is because acyl chlorides are very reactive and easily undergo substitution reactions. And the OH from the water molecule replaces with the chlorine. It produces a hydrochloric acid gas that we see when we test with the litmus paper. And there's also a carboxylic acid produced in the solution. And this is called a substitution reaction. Okay, so another test, another way that we can help distinguish organic molecules is just by their solubility. So what I mean by that is we take some water and we add the sample, our organic sample, to it, and we get the two layers, we shake it, and we see what happens. If they are soluble, once we've added the sample to the water and shake it, the two different layers disappear. Now, positive test for solubility in water is the two solutions are miscible, right? Miscible means that they can mix together without seeing two different layers after shaking. So if they're miscible, then we have solubility. Now, alcohols, amines, aldehydes, ketones, carboxylic acids, and amides are all soluble for their smaller compounds. Okay, from their carbons 1 to 2 or 1 to 4 or 1 to 3. So we've got small chains of any of these six. They're miscible in water, or they're soluble in water. Now, why are they soluble in water? What makes them special? What makes them special are hydrogen bonds. So each one of these molecules either has a nitrogen or an oxygen available with a lone pair that can form hydrogen bonds with water molecules. And you've also got, on most of them, you've got the actual hydrogen coming off that can form its own hydrogen bond with water molecules as well. So we've got all these hydrogen bonds happening. So they will form bonds as strong with water as water has with itself. So they will dissolve in water. Organic molecules that are soluble in water form hydrogen bonds with water. Okay, so when we carry out this test, we get a whole bunch of organic molecules that are insoluble in water. Now, so same thing, we take the water, we put in the sample, get the two layers, we shake, and we still get the two layers. Okay, they are immiscible. That means they're not able to mix anymore. They can't mix because they don't have the hydrogen bonds. And well, there's two reasons. They don't have the hydrogen bonds, or if you're the molecules we had in the previous slide and you had a hydrogen bond that enabled you to actually bond with water molecules, if you have more than 6 carbon atoms in your chain, you can't actually hold that bond anymore, because that whole chain of carbons and hydrogens is disrupts all the bonding in water, and so they're no longer soluble. So any of the original ones in the previous slide have 6 carbons and more, they're insoluble, but also all alkanes, alkenes, alkynes, haloalkanes, and esters are insoluble as water as well. Interesting about haloalkanes, because they do have what we'd say polar molecule, they have polar atoms in there, chlorines and bromines, but it's not the polar bonds that form that makes things dissolve in water, it's the hydrogen bonds, and they don't have hydrogen bonds. Okay, so carboxylic acids have a kind of distinctive odor as well, in that when you smell, or you take a whiff of a carboxylic acid, they have a really sharp smell. They attack the inside of your nostril. They make you want to sneeze, or just sort of, you just pull your head back. Apart from that as well, we go back to that butanoic acid that we talked about before. It's got a smell of rancid butter, or something vomiting. Particularly, it smells like baby vomit, and I guess that's because the milk, that fat inside the milk has been broken down into the butanoic acid. We've also got ethanoic acid, which is characteristic. It just smells of vinegar or salt and vinegar chips. That's very distinctive. Aldehydes and ketones. Aldehydes are interesting in that often an aldehyde smells like freshly cut grass. Now, the reason that happens is because there is a chemical that's found in plants that when plants get eaten, or they get cut, or they get broken, they release a stress chemical, and it's called cis-hex-3-enal. So it's an aldehyde, and it's the smell we associate whenever we cut grass. So it's actually an aldehyde, but notice it's got an alkene functional group as well. So we've also got ketones. They smell of nail polish. So the major component of ketones is nail polish. And actually, if you go away from nail polish, if you just have a very small smell of it, it does smell a bit fruity and sweet. So that's how we get that fruity, sweet smell when we get a small amount coming out from someone with ketosis when they're breathing it. And then another example here is this longer chain hexane-2-one that smells fruity. Again, look, lots of these longer chain ketones are found in things like red wine, and they produce some of the fruity flavors that people appreciate when they drink it. Okay, esters is another common one. Now they have a characteristically fruity or floral smell, but they're very strong fruity, very sweet. And you get these associated flavors, like this methyl butanoate smells like an apple. It does. You smell it, it smells like an apple. You might have made in class ethyl butanoate, and it smells like pineapple. As an aside here, both of these compounds are made from that extremely smelly butanoic acid, but they come out smelling really sweet and really tasty smelling flavors. And then you've got 2-methylpropanoate, smells like, or methanoate, smells like raspberry. And the last one here is 2-methylpropanoate, smells like banana. Look, there's like tens of other types of esters, and they smell like different fruits. And it's most probably the best one for identifying. So if you smell that really fruity smell of something, it's a good chance it's an ester, or possibly it could be a ketone. Okay, this is a new format for me. So look, share, like, and subscribe if you found the video useful, or if it's helpful, or even if you've enjoyed it. I'm going to continue making more videos that will go over chemistry concepts. I'm also going to do a set on physics concepts, and I'll do junior science as well. So yeah, don't forget to share this and subscribe. Press that like button too. See you on the next video.